Now we'll begin the problem set for Chapter 12. Chapter 12 involves liquids, solids, and intermolecular forces. So the only new equation for us will be the Clausius-Clapeyron equation. We'll also need an electronegativity chart to work some of our problems. To begin with, we're going to determine which molecules have dipole-dipole forces. So this is example 12.1. Which molecules have dipole-dipole forces? The first one is carbon dioxide. B is CH2Cl2, methylene chloride. And the next is methane, CH4. For carbon dioxide, we see that the electronegativity difference, or the electronegativity of carbon, is 2.5 and oxygen is 3.5. So let's look at that on the chart. Wrong chart. Carbon is 2.5 and oxygen is 3.5. Okay? So we have an electronegativity difference of 1 for each of these carbon-oxygen bonds. But since each of these carbon-oxygen bonds are canceling each other out, in other words, what's happening is the oxygen is pulling electron density away from the carbon in equal and opposite directions. So even though we may have a partial positive on the carbon and partial negative on the oxygen, since those forces are pulling in equal and opposite directions, that means that the molecule overall is not polar, and therefore the molecule doesn't have a permanent dipole. For methylene chloride, CH2Cl2, we have carbon, hydrogen, and chlorine. Carbon is 2.5, hydrogen is 2.1, and chlorine is 3.0. So we have electronegativity differences of, for the carbon and hydrogen, the electronegativity difference is 0.4. All right, and for the chlorine, carbon and chlorine, is what? So we had carbon is 2.5, chlorine is 3.0, so that's 0.5. So remember, anything 0.4 or less is considered nonpolar, but anything greater than 0.4 is considered polar. So these are polar bonds, and the chlorine is withdrawing electron density from the carbon. And we can draw a vector demonstrating that the electron density is going in that direction. So remember, these molecules are three-dimensional. They're not flat in most cases, and so, or at least in this case, and so because of these vectors, we have a resulting vector going right down the middle, and so we have a dipole for this molecule going in this direction. Okay, so that means we have a partial negative built up on this molecule on this side of the molecule. So this molecule does have a permanent dipole. For CH4, all of the bonds are carbon-hydrogen bonds, and therefore the electronegativity difference is just 0.4 because we have 2.5 minus 2.1. Therefore, there's not enough difference in bond polarity to create a polar bond, and therefore the molecule is not polar. Now let's consider Ci4, CH3Cl, and HCl. So the first one is a carbon with 4 iodines attached. Okay, so we have iodine here. So let's draw 2 of those in the plane of the board. Okay, let's draw one of them on a dash. That would be going into the board, going away from us. And the other on a wedge that would be coming out of the board. So this is a tetrahedral molecule, okay? So it looks similar to methane here, or methylene chloride, where each of these hydrogens instead would be an iodine. Okay, so let's look at iodine and see what the electronegativity is. So here we have iodine at 2.5 and carbon at 2.5, okay? So since there's no difference in electronegativity between carbon and iodine, that means this is a nonpolar molecule, so it doesn't have a permanent dipole. let's look at CH3Cl. Okay, so carbon with, let's draw a hydrogen let's draw a hydrogen this way and put another one in the plane of the board. And let's draw a hydrogen coming out. And let's draw the chlorine going back. Okay, the chlorine is on a dash. So this is also a tetrahedral molecule, so it looks similar to what we saw before. It's not flat, so it looks like this. Okay, so the chlorine carbon bond is polar because this is 3.5 minus 3. I'm sorry, 3.0 minus 2.5. So we have a difference of 0.5, and therefore we have a vector representing the polarity going toward the chlorine, and therefore this molecule has a partial negative charge with the resultant polarity going toward the chlorine. Now HCl has a difference in electronegativity of 2.1 versus 3.0, so we have a difference of 0.9, and that is large enough to be polar, and therefore HCl is polar.